Hello everyone and welcome to lecture. So you'll recall that for a level curve is not generally expressible with y as a function of x. So this is what we'll start going over for our first example of implicit differentiation. So this is so-called implicit differentiation in 2D, which is something you hopefully already know how to do from a Calculus 1 course. So you'll remember that if you have a curve in 2D, in general that curve can be expressed as a level curve of a multivariable function. Or a multivariable function z equal to some constant. A great example that you can always go with is the quadratic curves. So say like the ellipse or the circle or the hyperbola. I'll just do a circle of radius r to be, for simplicity. So we have a circle of radius r, and we know that this equation, a circle for the circle of radius r in Cartesian coordinates, is given by x squared plus y squared is equal to r squared. Or for fixed values of c, right, the level curve for the multivariable function f of xy is equal to x squared plus y squared. When you fix values of c, you get level curves. So in general, the level curve of a function could be some very complicated function f, but in the example of a circle, the function is just x squared plus y squared. And you might remember from a Calculus 1 course going over finding the derivative of the function y with respect to x. So you might say want to calculate the slope of the tangent line at some arbitrary point on the circle, say right here. So you might want to calculate the slope of this line right here, the tangent line to the circle, at some point on the circle. So what is y prime, or dy dx? All right, and it's not that simple because you have to go through and say we don't have y as a function of x for this curve. Now, it is possible to solve in this example for y as a function of x on the top half and the bottom half of the circle, but implicit differentiation gives us a much faster way of going through and evaluating this. Specifically using implicit differentiation from single variable calculus. We utilize what's called the implicit function theorem in mathematics. And we note that locally speaking, or if we kind of zoom in around any point on this curve, so you look from very close to the point on the curve, which corresponds to an x0 value, and a region down here around x0. So around any point right here in the open interval from negative r to r, we have the inverse function theorem which holds, which allows us to essentially solve for the derivative of this function, and we can solve for, say, y as a function of x in this small interval. this holds in general for more complicated functions, or much more general level curves. But what this allows us to do is write down, well, if y is expressible as some function of x, we can write that the equation of that circle is x squared plus f of x squared is equal to r squared, where y is equal to f of x. And if we go through and differentiate, this becomes 2x plus, and then we have to do the chain rule on this term right here. So it becomes 2 times f of x times f prime of x is equal to 0, because the x derivative of constant r is 0. And then we can solve for f prime, which is in fact equal to negative x over f of x, or negative x over y on the circle. So this is it. This is the expression that we get for this example by doing implicit differentiation. Now it turns out that this is something that we can do in general for general curves, general level curves. And not only that, it actually, what we're really doing here depends directly on the chain of dependence in the multivariable chain rule. So when we view this through that lens, it becomes clear what's actually going on here. In general, we have some multivariable function f that we're looking at a level curve of, and we're actually using the multivariable chain rule when we go through and do this right here, this process right here. So specifically for a general function, at any point, if I want to figure out what y prime is, we can do this exact same procedure, which will give us the slope of the tangent line even if we don't have y as a function of x. The main idea here is to think of this in the following manner. We take that f is a function of x and y of two variables. So the w, say, is the output of the function of two variables. And by the implicit function theorem, as long as we choose a small enough region surrounding our point x naught, this point, say right here, we'll call it r naught, which is some point x naught, y naught, that's on this curve. So the function that we have here, the multivariable function, is f of x, y. We're looking at a level curve of this function. So we're fixing w to be equal to c on this level curve. This is a level curve of the function. But then around the point x naught, y naught, in some small enough region around the point, the implicit function theorem guarantees us that we can solve for y as some function g of x. So what we have here is the following chain of dependence. We have that w depends on x, that w also depends on y, which itself depends on x. And what we have for our implicit equation on the level curve is that f of x comma g of x, because g of x is equal to y, is equal to c on the level curve. This is just coming from the definition of the level curve, which is that f of x comma y is fixed at c. So remember what these straight lines mean in this tree diagram for this scenario. This line right here indicates that w depends on x, so it's representing the rate of change of w with respect to x, the partial derivative of w with respect to x. This line right here represents the partial derivative of w with respect to y, and this line right here represents y prime, or the single variable derivative of y with respect to x, which is the thing that we're solving for. So if we differentiate both sides of this expression with respect to x, we take the total derivative with respect to x, we end up getting that f of the total derivative of this composition of functions with respect to x is the same thing as the total derivative of c. And the derivative of a constant is 0. And the derivative of this composition we compute using the chain rule. So it's the partial derivative of f with respect to x plus the partial derivative of f with respect to y times the single variable derivative, the total derivative of y with respect to x. Alternatively, you could say that df dx plus df dy partial f partial y times y prime is equal to 0. And if I subtract this term from both sides and divide by df partial f partial y, we get that y prime is equal to negative partial f partial x over partial f partial y. Or y prime is equal to negative fx over fy, which is a general formula for any level curve, solving for the rate of change of y with respect to x on the level curve. So this formula gives you the slope in the y-x plane of any level curve at any point on the level curve. Now, we'll just kind of check here in our example and make sure that our example is matching up with this directly. You'll hopefully remember this method right here from Calculus 1, but we want to verify that what we're getting with this general formula is effectively matching up, and it definitely is. Because if you look at this from the formula's perspective, right, the formula that we've derived for any level curve, this should be negative fx, which is the x partial derivative of our function f. That's going to be 2x over fy, which is the y partial derivative, which is negative x over y. It's exactly what we solved for before. So what we've just done is use the multivariable chain rule to directly essentially verify and extend very, very greatly our method of implicit differentiation. It makes it a lot easier to do this now for any function, no matter how complicated the function is. So we'll do another example just to kind of show this. Let's take the function or the level curve negative xy plus x squared plus y squared is equal to 1. So this is the level curve of this function of x and y. So our f of xy is this function right here. Specifically, it's the level curve when this function is set equal to 1. If you want to get a visualization of this, you can go ahead and do so in Desmos or some other tool. So I'll open up the Desmos window so we can take a look at this. X squared plus y squared minus x times y is equal to 1. And you can see that this is it's an ellipse that's rotated in some sense, rotated about the x-axis right here. So all of these points on this curve right here exactly correspond, right, to the this shape. This it's a level curve of this function right here. Specifically, we'll choose the point 1, 1. Now you can do this for any point on this curve, but the point 1, 1 will give us a nice calculation that we can go through and show in a very straightforward manner. So what we'll do is we'll take the point r naught to be equal to 1, 1, or x naught is equal to 1 and y naught is also equal to 1. So you could go through using calculus 1 and do implicit differentiation, but I think it's much simpler to use the formula that we just derived, which is that y prime is equal to negative fx over fy as long as fy is non-zero. So this is going to be negative times the partial derivative of this function with respect to x, which is negative y plus 2x, divided by negative x plus 2y. And there you have it. Right, this is exactly, for any point on this level curve, the value of y prime, or dy dx, the derivative of y with respect to x on the level curve. I think this is much faster and much quicker than going through and using implicit differentiation from single variable calculus, because you could go through and do that. So from calculus in so 1D calculus, doing implicit differentiation on this, you'd have to go through and use the product rule right here. This would be x derivative of this expression is going to be 1 times y plus y prime. The x derivative of this expression right here is going to be 2x. And the x derivative of this expression right here is going to be 2y times y prime. And the x derivative of 1 is just 0, because the derivative of a constant is 0. And then you can factor out the y prime term to get that. This is going to be negative y plus 2x plus this should be y prime times x. Did the product rule a little bit wonky there. This should be the derivative of x, which is 1 times y plus x times the derivative of y, which is y prime. So that then gives us, when we factor out y prime, it'll be negative x plus 2y times y prime is equal to 0. And if you solve for y prime, you get that y prime is equal to negative y plus 2x divided by negative x plus 2y, which is exactly what we attained using implicit differentiation for multivariable functions, but this method is a lot faster and it includes less algebra. So I would definitely say that that's a preferred method for going through and doing this derivative calculation. This is a common theme that's going to arise in this course, is that typically what takes a few steps in Calculus 1 is very, very, very fast in calculus, multivariable calculus. So if we go through and try to get the tangent line, say, at this point, and remember, we can do this at any point on this curve, but we're going to stick to this point 1, 1, because it's going to give us nice calculation when we go through and calculate. The first thing that we need for the tangent line is the slope of the tangent line at the point, or y prime at the point r naught. This is going to be equal to negative 1 plus 2 times 1 over negative 1 plus 2 times 1, which is just equal to negative 1. So the slope of the tangent line at this point, r naught, is equal to negative 1, and thus the equation of the tangent line, or y is equal to m times x minus x naught plus y naught, is going to be equal to negative x minus 1 plus 1. And this should be the equation of the tangent line to this curve. So if we go through, we open up the Desmos window, and we add a new plot. We type in y is equal to negative times x minus 1 plus 1. Sure enough, we get exactly that. At the point 1, 1 on this curve, the tangent line is exactly this expression right here. And we can kind of zoom in here to see it more clearly, but this is clearly the correct equation of the tangent line at this point, and we got it just by using this new multivariable implicit differentiation. So we can see, hopefully, that this is a very powerful method. This can be applied for any level curve and will allow you to get the slope of that level curve in the xy plane. As always, for all of our methods, we want to be able to kind of generalize this and go to see what this implies about 3 variable functions and higher number of variable functions. And sure enough, we can directly extend this method to solve for partial derivatives on level surfaces as well. And it turns out that this method that we're using for implicit differentiation can be applied to functions of any number of variables. We can use this to generalize to any number of variables that we might want to consider. But for right now, let's stick to functions of 3 variables. So you'll remember that in general, a level surface of a function of 3 variables is some surface that gives us a constant value for the function. So f of x, y, z, say, is equal to some fixed value c. But this is the x-axis, the y-axis, and the z-axis. And similar to the 2D scenario, it's conceivable that we could have a point on this surface. At this point right here, say, we'll call it R naught, just like before, where R naught is some fixed point x naught, y naught, z naught that's on the surface. And we could want to say get the tangent plane to R naught. So the z partial derivative and the x partial derivative exactly at that point R naught. Maybe looks like the x partial derivative of z looks like that on the surface, and the y partial derivative might look like that on the surface. So the tangent plane at that point is some plane so a surface in 3D that's tangent to this level surface. So the question is how to find partial z partial x and partial z partial y on the level surface. And it turns out that we can directly go through and do this using exactly what we did before with implicit differentiation. It's actually a very nice formula. We have that the implicit function theorem holds for multivariable functions. And specifically, if you kind of zoom in close enough around any point where the partial derivative of f with respect to z is non-zero in the region, so around the point R naught, and you can express z as a function of x and y. As long as this is true, the implicit function theorem guarantees for us that we can find some expression for z as a function of x and y. This is a lowercase. It's different than the capital F function that's giving us our level surface. And so what that means is we have a chain of dependence. So the tree diagram for this scenario is saying that, well, if w is equal to f of xy, say, sorry, not f of xy, but f of xyz. It's a function of three variables. And z is a function of x and y. The tree diagram for this example is that w depends on z, but it also depends possibly independently on x and on y. And both x and y also depend on z. So z depends on y and z depends on x. And you'll notice that I put z higher than x and y because it still depends on x and y. But this is the correct tree diagram for this scenario. And what that means is that on the level surface, where w is fixed at some c value, the level surface is given by capital F of x, y, and then z, which is lowercase f of x and y, is equal to c. So this is the equation that's true on any level surface. So to get the partial derivatives of lowercase f with respect to x and lowercase f with respect to y, because dz dx is the same thing as fx, and dz dy is the same thing as fy. We need to go through and use the chain rule. We take the partial derivative of both sides of this expression with respect to x. So the left-hand side is the partial derivative of this composition of functions, and the right-hand side is the partial derivative of the constant c. From the multivariable chain rule, on this tree diagram, you see that there's two paths of dependence of w on x. It's this path of dependence right here and this path of dependence right here. So the correct way to take the partial derivative is to take the partial derivative of f with respect to x, and then also then take and add to this the partial derivative of capital F with respect to z, and multiply by that the partial derivative of lowercase f with respect to x. And that's equal to 0. So we can solve for what we're looking for, which is df dx. And df dx is then equal to negative partial f partial x over, and let me be very clear here, this should be lowercase f. We're solving for this derivative of lowercase f with respect to x over the partial derivative df dz, or in short, it's negative fx over fz. This is dz dx. And we've obtained a very, very straightforward method of getting dz dx. And I really encourage you to go through this derivation and do the exact same thing, but do it for dz dy as well, the y partial derivative of z. The computation is very, 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 very similar, and the way that it kind of comes from is almost the exact same thing as this, only you want to go through and take the partial derivative of this expression with respect to y. But the formula that you get is that dz dy is equal to negative fy over fz. So we've obtained two very nice formulas for implicit differentiation that we can always use whenever we have a function of three variables and we want to figure out the rate of change of one of the variables with respect to one of the other variables that obey that implicit relationship. So let's go through and look at an example. Specifically, we'll consider the level surface x squared plus y squared plus z squared plus xy plus yz plus xz is equal to 2. And we'll consider this on so, if you want to, we'll open up the Geogebra window, and probably the best thing to do is to kind of visualize what this level surface looks like. So let's just take a look at it right now. So you see, this is the Geogebra window. We're plotting out the surface the level surface x squared plus y squared plus z squared plus xy plus yz plus xz is equal to 2, then you see that it's sort of like an ellipsoid that's been rotated. And we want to go through and calculate the tangent plane at some point, maybe if you want to figure out dz dx and dz dy. So let's fix a point, take a certain point on the surface. It's important to emphasize, I know I keep saying it, but this can be done on any point on the surface. We'll just pick the point 1 over the square root of 3 for x, 1 over the square root of 3 for y, and 1 over the square root of 3 for z. This is a point that satisfies this level surface equation. So it's on this level surface. And we want to go through and use the formula that we just derived, and they should apply to this expression right here. So dz dx, and remember that this entire expression is that multivariable function that we're talking about. We're talking about the level surface of this multivariable function set equal to 2. It should be equal to negative fx over fz which is negative 2x plus y plus z divided by fz, which is 2z plus y plus x, and dz dy should be equal to negative fy over fc, which is negative 2y plus x plus z divided by 2z plus y plus x. So in general, for points on this level surface, for any point in the level surface, this would be how you get the partial derivative of z with respect to x and the partial derivative of z with respect to y. So we can take these two expressions, and what we're really interested in is what this value is at the specific point on the surface that we're talking about. So dz dx at the point r0 is going to be negative 2 times 1 over the square root of 3 plus 1 over the square root of 3 plus 1 over the square root of 3. And this is going to be divided by 2 times 1 over the square root of 3 plus 1 over the square root of 3 plus 1 over the square root of 3. And the numerator here is the same as the denominator here, so this is just going to be negative 1. And likewise, dz dy at the point r0, I'll let you plug in for this one. You plug in right here. This will also be negative 1. Which means that the equation of the tangent plane remember from the lecture on linearization and the tangent plane, is going to be equal to z equal to m times x minus x naught plus n times y minus y naught plus z naught, or z is equal to negative x minus 1 over the square root of 3 minus y minus 1 over the square root of 3 plus z naught, which is 1 over the square root of 3. So this expression right here should give us the valid tangent plane on this level surface using the information about the partial derivatives that we obtained using implicit differentiation. So let's open up the Geogebra window and just kind of verify this. So z is equal to negative x minus 1 over the square root of 3 minus y minus 1 over the square root of 3 plus 1 over the square root of 3. And sure enough, that on this level surface right here at the point 1 over root 3, 1 over root 3, which is exactly this point right here, this plane that we calculated to be the tangent plane is giving us exactly that. We have that this is 100% the tangent plane to this surface at that point. So the idea here is that in general, if you have an implicit relationship like this, this method of implicit differentiation is in fact the correct way of going through and calculating the relationship between partial derivatives on this plane, or on this surface. The last example that we're going to talk about today in lecture is going to be an application to electrical engineering. And specifically that's to what are called equivalent resistance of resistors in parallel. So in general, if you have a circuit with electrical current running through it, you model things that use up current or use up voltage from a voltage source on the line as resistors. And those resistors can be either in series, or one after another, or in parallel, which means the current splits and hits each resistor individually. And then maybe comes back together at a certain point. And the circuit is completed. So let's say that resistor 1 is this R1 right here. Resistor 2 is R2, and resistor 3 is R3. So when we apply what are called Kirchoff's laws, which are from physics, and essentially tell us about the conservation of energy throughout the circuit. They guarantee that energy is conserved as current flows through the circuit. We end up having the following result. We can actually replace this circuit right here with a different, simpler circuit with one resistor on it, one resistor of a resistance called Req, where Req is the equivalent resistant of the circuit, the equivalent resistance of all of these resistors. Now, for resistors in series, or one after another, the equivalent resistance is just the addition of each resistance. But for resistors that are in parallel, the equivalent resistance actually obeys what's called an inverse law. So 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So this is what the resistance law is for the equivalence resistance for circuits, for resistors that are in parallel. What's nice about this computationally is that if you can solve for the current through this circuit, which is much easier than solving for the current through this circuit, then you're solving for the actual current that traverses this line. And you can use this to simplify many different calculations. But the idea here is that this is actually an implicit relationship between 4 variables. Right? If you say that, well, instead of using R1, R2, R3, we'll kind of simplify a little bit. We'll say that Req is the output, say, W. And then we'll just call R1X, R2Y, and R3Z. So the implicit relationship that we have between our variables from the parallel law is going to be that 1 over W is equal to 1 over X plus 1 over Y plus 1 over Z, where W is the equivalent resistance and X is R1, Y is R2, and Z is R3. So what we can do is we can go through and directly use what we've kind of been talking about, which is the idea of implicit differentiation, to go through and solve for the rate of change. Say, let's say you might be interested in the rate of change of Req, or the equivalent resistance, with respect to R1, or the rate of change of Req with respect to resistor 3 or resistor 2, because you're changing certain elements of your circuit. Let's say one of the elements is something you're working on, and you're changing one of the elements' resistance by a certain value. So what you can do is, in this expression right here, if you rewrite this as 1 over W, and actually I'll probably do 1 over X plus 1 over Y plus 1 over Z minus 1 over W is equal to 0. You have a function of 3 variables, or 4 variables, X, Y, Z, and W, but W itself is a function of X, Y, and Z, because it's just the equivalent resistance. So this relationship, this implicit relationship, is giving you a functional dependence of W on X, Y, and Z. The tree diagram for this example is given by W depends on X. Not X. This F right here depends on X, on Y, and on W, or on Z, and on W. And W itself depends on X, on Y, and on Z. So if you want to go through and derive what, say, dw dx is, remember dw dx is the same thing as the partial derivative of Req with respect to R1. The formula from our implicit differentiation, and you can get it directly from this tree diagram using a similar method to what I showed before, is going to be negative fx over fw, and the partial derivative of f with respect to x is going to be the partial derivative of 1 over x. That's negative 1 over x squared divided by the partial derivative of f with respect to w, which is going to be 1 over w squared. This is equal to then just w squared over x squared, or w over x squared. And you can do the same thing for dw dy, dw dz, to find the rates of change of the equivalent resistance with respect to resistor 2 or to resistor 3. So it's a very quick way of going through and calculating. Now, luckily, this is not always possible to solve for your the w for the other examples we talked about. For a general implicit function, I should say. So for a general f, it's not always possible to solve for w in terms of x, y, and z. But the resistor example is nice because we can actually check this result to make sure that this result is correct. And the check is a little bit long. It involves essentially solving for w. So to check our work from implicit differentiation, we can go through and say, well, 1 over w is 1 over x plus 1 over y plus 1 over z. And this is the same thing then as 1 over w. If I bring this entire thing right here to common denominator, I'm going to have to multiply this term by yz over yz. So you get yz over xyz plus xz over xyz plus xy over xyz, or yz plus xz plus xy over xyz, which means that w is in fact equal to xyz over yz plus xz plus xy. This is the longer method of getting the rate of change of these equivalent resistance. But if you solve for the equivalent resistance in terms of resistor 1, 2, and 3, which I've done right here, to calculate any one of the partial derivatives, say like dw dx, you can just go through and use the normal derivative laws that you know from calculus 1. Say the partial derivative of this expression with respect to x is going to be, I'm going to use the quotient rule here. So it'll be yz times yz plus xz plus xy minus xyz times the partial derivative of the denominator with respect to x, which is z plus y, divided by denominator squared, and this is definitely kind of long, so if we go through and see here that you have, it's going to be y z squared plus xyz squared plus xzy squared minus xyz squared minus xzy squared, all over our denominator. And luckily we have some cancellations in the numerator here. You have that this is canceled by this term, and this term is canceled by this term. So what you're left with is the exact value of dw dx, which is that dw dx is equal to yz over yz plus xz plus xy squared. And this is how you would go through and actually, directly solve this equation without using implicit differentiation. Now you might say that there's a problem here, a slight problem, because this expression doesn't match up with what we found before, but actually it does match up with what we found before, because you'll remember that before we found what? We found that dw dx is equal to w over x squared. And if you plug that in to kind of verify this, that this is giving you the exact same thing, you remember we solved for w as xyz over yz plus xz plus xy. This is just plugging in for w over x squared. And this expression, sure enough, when the x's will cancel out and leave us with just yz over yz plus xz plus xy squared. Alright, so this expression is much shorter, more compact, and nicer, I think, than this expression that we obtained by directly going through and solving for w and then doing the partial derivative. The idea, though, is that all three of these are equal to one another, and this is, you can use either formula to go through and get this rate of change of the equivalent resistance. So I encourage you to kind of play around with this example a little bit and to directly go through and do this process for dw dy and for dw dz. So and also remember that, right, these variables have meaning. In this case, this is the rate of change of Req, the equivalent resistance of a circuit, with respect to R1, whereas dw dy is the rate of change of Req with respect to R2, and dw dz is the rate of change of Req with respect to R3. So this is a very, very nice example coming directly from electrical engineering, and it's how you would, in practice, use either implicit differentiation, but more generally, the idea of a partial derivative. If you have some equation that holds from physics or engineering, you can directly use implicit differentiation and partial differentiation to figure out the rate of change of certain quantities in that expression. But that's it for lecture today. Thank you very much for tuning in, and I hope you have a great day.